All right, welcome back to the deep dive. Today we are swapping out our surgical loops for the electron microscope. We are performing a hyper-technical scrub into the orthopedic engineering laboratory. Specifically, we're targeting the core of total knee replacement, or TKR, and unicompartmental knee replacement longevity.
Hmm.
We're talking pure, dense, and essential tribology, the science of wear, friction, and lubrication, as demonstrated by wear simulation studies. This data is the difference between a knee lasting 10 years and, well, lasting 30 years.
It really is. It's the ultimate backstop to our work in the operating room.
Right.
For us, the clinical mission isn't just about achieving perfect alignment and stability today.
Right.
It's about engineering that to sustain a lifetime of loading.
Mm.
We need to understand exactly how the engineer's subtle material and geometric choices,
Mm.
like the degree of cross-linkage in polyethylene or the radius of curvature in the femoral component affect function, and ultimately premature wear in vivo.
And to anchor this discussion in clinical reality, let's start with the traditional benchmark. We always cite that 1 million gait cycles is the standard estimate for a full year of activity.
That figure is, quite frankly, a historical relic. It's based on highly sedentary cohorts from decades ago. We're now seeing increasingly younger, healthier patients receiving TKRs.
And those younger active patients, the ones in their 50s and 60s who expect to, stay highly mobile, they are clocking in well over 2 million steps per year.
Easily.
We're looking at potentially 4 times the wear demand that the first generation of simulators was even designed to measure. This just highlights the truly intense biomechanical gauntlet we put the ultra-high molecular weight polyethylene, the UHMWPE bearings through.
And this clinical reality is precisely why we've moved light years past historical simple tests. Think back to the basic pin-on-plate or pin-on-disc configurations.
Yeah.
Those tests were excellent laboratory tools for defining raw material characteristics, like friction coefficient or hardness. But their outcomes just consistently failed to correlate with what we actually saw failing in patients.
So why the failure to correlate? What was missing?
They simply couldn't replicate the crucial multifactorial in vivo environment. They didn't capture the changing load vector, the complex internal-external rotation, the presence of biological lubrications.
Synovial fluid.
Exactly, synovial fluid, or the highly specific cyclic joint kinematics. We learned very quickly that wear in a TKR isn't a linear phenomenon of simple friction. It's a nonlinear problem driven by the geometry of the destruction.
So let's unpack the magnitude of this shift. If the pin-on-disc test is like trying to measure the friction on a toy car, the modern knee simulator is the most sophisticated multi-axis Formula One testing rig you can imagine.
That's a great way to put it.
It has to manage, a half dozen variables simultaneously, which is why we call this a multifactorial problem.
It is the ultimate multivariate analysis. The survival of that bearing in the patient is a product of at least 6 interacting factors. You've got the bearing design itself, the molecular material choice, lubrication, the specific component position that we, the surgeons, choose.
Right, our part in it.
Our part. And there's the patient's actual loading pattern, their body weight, and most importantly, the complex joint kinematics. A robust simulation isn't just assessing one factor, it's assessing the nonlinear interactions among all of them.
And this need for a massive, realistic envelope of testing brings us to sort of the future of simulation strategy, the safer paradigm, the stratified approach for enhanced reliability. Traditionally, most studies focused almost exclusively on simulating standard, idealized gait, which we now know is a very narrow slice of reality.
Safer just throws that narrow focus out the window. It demands that we account for the entire messy, real-world envelope of conditions.
Yeah.
It's an acknowledgement that, perfection doesn't exist in the OR or in the patient's lifestyle.
So what does safer specifically dictate we have to test for? What are the strata?
It dictates we stratify and test variations in 4 key areas. First, variations in surgical delivery. This means testing implants installed in slight malrotation, or maybe 2 degrees of varus or valgus, or slightly off-center, the inevitable deviations we see.
The real world?
The real world.
Mm-hmm.
Second, variations in kinematics, moving beyond simple walking to things like stair climbing, deep kneeling, or rapid turning. Third, variations across the patient population, so testing obese patients, or those with muscle weakness affecting their gait. And finally, variations in biomaterial degradation over time, particularly long-term oxidative aging.
I just picture SAFER as this massive, expensive statistical matrix.
Yeah.
You're trying to test every combination of a malaligned implant in a heavy patient, doing a weird activity using aged poly. Trying to do that purely through physical testing seems impossible.
It is. The source material is very clear that testing under this wide portfolio of stratified conditions cannot be achieved using experimental simulation alone. The sheer number of physical tests is prohibitive. We'd spend a decade and millions of dollars running the equipment 204 to 7.
So that's the inflection point. That's where we have to pair the physical lab with computational modeling.
Exactly. This is where we bring in the indispensable power of computational modeling.
And that's where we get the heavy hitters, finite element analysis, or FEA. When we use this modeling, what specific data are we getting that the physical simulator just can't provide?
FEA gives us critical metrics that are virtually unattainable experimentally. The two most important are internal contact stresses, so the pressure map across the bearing surface, and most crucially, the distribution of cross shear.
Ah, cross shear. We'll be coming back to that.
We will. We can computationally map exactly where and when the polymer material is being loaded and twisted simultaneously.
So understanding stress and cross shear is the ultimate tool. It's the difference between seeing a wear scar on an explant and knowing the microscopic mechanism that caused the polymer chains to fracture in the first place.
Precisely. But, and this is a huge but, we have to deliver the crucial caveat that needs to be drilled into every engineer and resident.
Which is?
Computational models are only useful if they are adequately validated.
Right. And the validation has to occur at the extreme range of conditions, not just in the easy middle ground.
Exactly. If you just validate your FEA model under perfect standard low-load gate, the moment you input a 10-degree malrotation or a massive liftoff event, which SAFER demands, the model might fail completely. It would be operating outside of its experimentally validated envelope.
So you have to physically test the edges of that envelope to make sure the computer's predictions are still true. It's like checking a bridge in a hurricane, not just a gentle breeze.
That's a perfect analogy.
Yeah.
If your pristine boundary conditions don't reflect the sloppy real world, your predictions are worthless.
Speaking of rigor, let's talk about the simulator mechanics themselves and the ongoing debate around international standards. I call it the ISO wars. If you look at figure 23.1, you can see the complexity. Most simulators use 6 degrees of freedom.
Yes. 4 of those are actively controlled by the machine. Axial load, anterior-posterior or AP motion, internal-external or IE rotation, and flexion extension.
And then 2 are passive or fixed. Abduction, adduction, and medial lateral displacement. The core debate, the ISO wars, is all about how we govern those active axes, right?
Correct. Specifically AP translation and IE rotation, because the control method dramatically dictates the wear rate outcome.
So what are the two camps?
Well, you have 2 major international standards. First, there's force control, which is ISO 14243-1. In this setup, the simulator applies known forces or torques, and it often uses simple spring elements to represent the soft tissue constraints you'd find in vivo.
Okay, so the rationale is to better represent how a specific implant behaves in a constrained, but not rigidly fixed environment. But I've always had an issue with this. My analogy is that using simple linear springs to mimic the body's soft tissues is like trying to model a Ferrari's Baptist suspension with 2 rusty, slinky springs.
It's a fantastic analogy because it's true. Soft tissues ligaments, the capsule, have wildly complex nonlinear force displacement relationships.
So what's the risk?
The risk is if a design has poor inherent geometric constraint, the simplicity of that linear spring system might actually let the implant wiggle around in an unphysiologically aggressive way, which of course drives up the wear rate.
So it effectively punishes bad designs, which you could argue is a good thing.
You could. Now, the other standard is displacement control, or ISO 142433.
The opposite approach.
The exact opposite. Here, the movements, the AP translation and IE rotation, are directly prescribed and rigidly controlled. The machine is programmed to move the femoral component by, say, precisely 5 millimeters, regardless of the implant geometry.
So you get pristine repeatability, clean data. But the downside is you might be forcing unphysiological motion onto a high conformity bearing.
Exactly. Imagine driving a car where the steering wheel is locked and the car is programmed to turn a specific radius regardless of the road. If you force a highly conforming constrained bearing to undergo an aggressive 10 millimeters of AP displacement, you're pushing it outside its natural geometric constraint and generating extremely high non-clinical contact stresses.
Which could give you artificially high wear. So this all leads to the clinical implication from studies like Shrinka et al. What did they find?
They found that low-conforming, fixed-bearing knees showed significantly higher volumetric wear under load control compared to displacement control, even when the overall rotation was similar.
Wow, that's a huge finding.
It's paramount. It tells us that the implant design dictates the appropriate testing method. If you use load control on a design with poor stability, the simulator will mercilessly punish it, revealing its weakness.
And displacement control might flatter that same poor design by physically stopping it from failing.
Correct. The takeaway for anyone looking at implant data is transparency. If a company boasts a low wear rate, your first question has to be, was this tested under force control or displacement control?
Because each method introduces its own bias.
A huge bias. And we have to remember, both standards describe an idealized gait for an idealized patient with perfect surgery. This ignores the safer reality of clinical variability completely.
Okay, so let's move past the testing machine and drill down into the kinematics themselves. If oxidation was the enemy 20 years ago, today, the specific geometry of motion, the kinematic profile, is the true modern aggressor.
It absolutely is. Wear rates are acutely sensitive to the magnitude of that AP displacement and IE rotation.
And this is why those early studies had such low wear rates, right? They were using these benign, low kinematic protocols.
Exactly. As soon as labs started inputting more realistic, aggressive motion profiles, the wear rate shot up, and they started aligning much better with the clinical data we were seeing in active patients.
So let's use the specific data points from those fixed-bearing knee studies. High kinematics is defined as what? 0 to 10 millimeter AP displacement and plus or minus 5 degrees of IE rotation.
That's the standard. And they then perform these strict kinematic restriction tests.
And the first result was logical, but still striking. They just reduced the AP displacement by half, down to 0.5 millimeter.
And they saw a two-fold reduction in the mean volumetric wear rate, which makes sense. Less sliding distance, less wear. It's proportional.
But here's where it gets really interesting and nonlinear. They kept that reduced 0.5 millimeter of AP travel, but they also halved the IE rotation to plus or minus 2.5 degrees.
And the result was an astonishing four-fold reduction in wear rate compared to the standard high kinematic.
A four-fold reduction. So that small change in rotation had a massive, disproportionate effect on wear.
An exponential effect.
Yeah.
And that exponential drop is the undeniable fingerprint of cross shear.
Okay, so we have to spend time on cross shear. It's the fundamental mechanical enemy of polyethylene in the knee. Explain the concept from an engineering perspective. Strain hardening and softening.
So when polyethylene slides consistently in one direction, let's say purely AP, the long, spaghetti-like polymer molecules align themselves along that sliding path. This process is called strain hardening.
Okay.
It actually makes the material tougher and more wear-resistant along that specific line.
It's like trying to cut a thick rope by pulling the knife along its axis. It's hard to do.
Perfect analogy. But here's the vulnerability. In the direction transverse to that sliding sew, perpendicular to the AP motion, the material simultaneously becomes strain-softened and weak. So when you introduce IE rotation, it creates a frictional force that's transverse to the main sliding direction. And this force attacks the polyethylene in that weakened, strain-softened state.
So the combination of AP sliding, which makes the poly weak on its sides, and the IE rotation, which attacks those weak sides,
leads to an explosion in wear. That's the fourfold reduction you see when you have the rotation. The multi-directional motion dramatically increases cross shear, and material just gets ripped away.
And a fixed-bearing knee, where all that crazy motion happens on one surface, is just the perfect storm for this effect.
It's the perfect storm for maximizing cross shear.
So if cross shear is the enemy in the lab, then condylar liftoff is the clinical disaster that proves this mechanism happens in vivo.
It is. Fluoroscopic studies have proven that liftoff happens in real patients during gait. So to study this, they set up this brilliant catastrophic simulator test.
What did they do?
They simulated a 1 millimeter lift of the lateral condyle during every single gait cycle, just 1 millimeter. They did it by applying a dynamic rotational moment on the adduction axis. It simulates a tiny moment of soft tissue imbalance.
A minor surgical imperfection, and the outcome.
The outcome was terrifying. They saw a significant wear increase in both fixed and mobile bearings. But the most crucial data point for us in the OR was that the typical, well-documented advantage of mobile bearings, their lower wear rates, it completely disappeared under liftoff conditions.
Wow.
That is the ultimate demonstration that material science cannot overcome poor stability. 1 millimeter of kinematic instability instantly negated the complex, expensive engineering advantage of the mobile bearing.
So what was the mechanism?
It was a dramatic, uneven loading. It focused all the axial load onto a tiny area, which drastically increased the contact stress and escalated the cross shear on the overloaded medial condyle.
So the clinical application is just crystal clear. Any malalignment, any ligament imbalance, any soft tissue laxity, anything that lets that condyle lift off, it just tanks the wear performance.
It does. We can't rely on the polymer or the design to save us from sloppy soft tissue balancing. That one little imperfection sets the biological clock on the implant immediately.
Let's pivot now from the motion to the components themselves, specifically fixed versus mobile bearings. If you look at figure 23.2, you can see the two major schools of thought.
Right. In the fixed bearing, figure 23.2a, the poly insert is locked into the tibial tray. This means all that complex, multi-directional movement, all the cross shear, is concentrated at that single superior articulation with the femur.
It maximizes that strain softening effect we just talked about.
Exactly. Then you have the rotating platform mobile bearing in figure 23.2b. The fundamental beauty of this design is that it mechanically decouples the motion.
It adds a second interface.
It does. It permits rotation at a second inferior interface between the insert and the tibial tray.
And that decoupling is the mechanical magic trick.
It is. It takes that complex, chaotic, multi-directional motion coming from the femur, and it breaks it down into simpler, more manageable uniaxial motions at both the superior and inferior interfaces.
So instead of one surface dealing with simultaneous rotation and translation high cross shear, the top surface handles the AP sliding and the bottom surface handles the rotation.
By converting that aggressive input into two cleaner, largely uniaxial motions, you minimize the strain softening and you dramatically reduce the overall cross shear. And studies have confirmed this leads to lower wear rates compared to fixed bearings under the same inputs.
Okay, now let's dive into the great engineering paradox in knee design. Conformity. This is where we have to go back in time a bit.
Historically, say 20 or 30 years ago, we were battling aggressive delamination. Early UHMWPE, especially the gamma-sterilizing air kind, was prone to this structural fatigue. Oxidation made it brittle.
So what was the design solution?
The solution was higher conformity, a deeper dish where the femoral component fits snugly against the tibial insert.
And the goal was purely mechanical. Spread the load over the widest area possible to reduce the peak contact stress.
Exactly, to delay or eliminate the risk of structural fatigue. It was a life-saving trade-off for a poor material.
But the fascinating modern turn is that our materials are so much better now. We've basically eliminated the oxidation problem. And this has allowed designers to revisit low-conformity designs.
It has. And what they found, in studies contrasting traditionally curved inserts with completely flat inserts made from the identical modern UHMWPE.
They found that the flatter, less conforming design showed a significant reduction in surface wear.
Correct. Which seems completely counterintuitive if you only think about stress. Low conformity increases contact stress.
Wait, I have to pause there. That's like telling a resident that a flat tire wears better than an inflated one. If increasing the pressure on the polymer reduces the wear, the mechanism of wear must have fundamentally changed. So how do we explain this?
The explanation comes back entirely to the control of cross shear. While high conformity spreads the load, it also rigidly constrains the motion. So when the knee inevitably rotates, the high conformity resists that motion, and it forces high cross shear forces onto the material.
So the high conformity fights the patient's natural rotation, and that fight generates aggressive cross shear on the surface.
Precisely. Conversely, a low-conforming, flatter design can accommodate that rotation and translation much more easily. It might momentarily increase the contact stress, but it minimizes the strain softening effect because the material isn't being twisted in place.
So we've shifted from high conformity to fight delamination to low conformity to fight surface wear. But this introduces a huge clinical vulnerability, doesn't it? Less conforming bearings need perfect, soft tissue constraint.
That is the critical warning. If you put a low conformity bearing into a patient with lax ligaments, you are virtually guaranteeing condylar liftoff and excessive kinematics. That design is not suitable for all patients.
The low wear benefits from the lab are entirely contingent on a tight soft tissue envelope in the OR.
100%.
And briefly on unicompartmental knee replacements, or UKRs, they follow the same rules, right? But with an inherent asymmetry.
A profound asymmetry. Simulator studies of medial and lateral UKRs consistently show higher wear on the medial bearing compared to the lateral. This just confirms the biomechanical reality that the medial compartment carries the vast majority of the load.
And the conformity effect holds true there as well.
It does. Studies comparing the mobile Oxford bearing with a low-conforming fixed bearing confirm the TKR trend. Lower conformity resulted in lower wear rates.
And what's the final insight on UKRs versus TKRs?
It's fascinating. The combined wear for fixed UKRs was significantly lower than that of a comparable fixed-bearing TKR, which suggests that if you can successfully isolate the replacement to one compartment, you get a substantial wear advantage, probably due to the stability provided by the remaining native tissues.
All right, let's move to the molecular battleground. While geometry determines how the material fails, the material science determines its inherent resilience. And the primary villain in early TKR failure wasn't friction, it was oxidative degradation.
And this failure stemmed directly from a flawed manufacturing step: sterilization. The original method was gamma sterilization in air.
So what's wrong with that?
Well, gamma radiation is a high-energy process. It breaks down contaminants, but it also breaks the polymer chains of the UHMWPE, creating highly reactive, unstable molecules called free radicals.
And when those free radicals meet the oxygen trapped in the packaging?
They immediately combine, and this reaction causes massive, accelerated oxidative degradation. It systematically reduces the mechanical properties of the poly, making it weak and brittle over time.
And we saw the proof of this with the shelf aging evidence, right?
We did. Studies compared poly aged for 1 year versus 7 years. The 7-year samples had a much higher oxidative index, with the peak oxidation occurring just below the articulating surface.
And that subsurface oxidation is the death knell.
It is. During simulator tests, they saw subsurface cracking on the 7-year aged bearings starting at just 1 million cycles. That damage progressed to full-blown delamination after 5 million cycles, which perfectly matched the failures we were seeing clinically.
It was a time bomb installed during manufacturing. The solution had to be molecular, and that's where we adapted tech from the hip world: cross-linked polyethylene.
The fundamental mechanism is to take the same radiation dose, but do it in an inert environment, without oxygen. This creates many chemical cross-links between the polymer chains. This highly cross-linked structure fundamentally resists that aggressive, multi-directional wear the cross shear.
But the process itself creates more free radicals, so you have to deal with those, and that's where remelting comes in.
Correct. You have to heat the material above its melting point. It's a precise process, but it allows those residual free radicals to recombine or dissipate, ensuring complete oxidative stability.
And the clinical results for this stabilized cross-linked material were, well, transformational.
They were. In an aggressive aging study, the conventional aged poly failed by 4 million cycles.
But the aged, moderately cross-linked material,
It showed no damage whatsoever after 5 million cycles. And in extended testing, it showed no damage even after 10 million cycles. That's a lifespan improvement from a 4 million cycle failure to a 10 million cycle damage-free survival. It largely solved the material aspect of the wear problem.
Now here's a technical nuance. We adopted moderate levels of cross-linking for the knee, not the high levels we see in hips. Why the difference?
It's the constant trade-off in polymer engineering. High cross-linking dramatically improves wear resistance, but it also inherently reduces the material's toughness, its resistance to fracture. In the hip, where contact is conforming and load is predictable, that's an acceptable trade-off.
But in the knee, with its high impact events and risk of liftoff, you need structural integrity. High cross-linking could risk the material becoming fragile and just shattering.
Exactly. We need to balance wear performance with robust structural integrity. And that concern led to the next innovation: vitamin E stabilization.
This tries to get the best of both worlds, right? The wear performance of cross-linking while preserving the toughness.
That's the goal. The engineering is highly elegant. Instead of using high heat to deal with the free radicals, you blend vitamin E alpha tocopherol, a powerful antioxidant, into the UHMWPE.
And it acts as a radical scavenger.
An immediate radical scavenger. It neutralizes any free radicals generated during radiation. And crucially, it allows you to preserve the material's crystallinity and toughness, avoiding that heat cycle for remelting.
And the initial findings are promising.
Very promising. Studies show improved wear performance compared to conventional poly, under standard and aged conditions. It appears to offer the best of both worlds.
Yet,
but still relatively young. We need expensive simulator studies across the entire SAFER envelope, plus long-term biologic studies, before it completely supplants the tried-and-true, moderately cross-linked material.
okay, finally, let's quickly cover the search for alternative bearing surfaces, beyond the standard cobalt-chrome femoral component.
The initial push was towards ceramics. Alumina and zirconium-based ceramic femurs have shown significant reductions in wear rates, better hardness, lower friction.
So why aren't all femurs ceramic?
The same old issues: Toughness for manufacturing complex shapes, the much higher cost, and the complexity of fixation. Similarly, oxidized zirconium, a surface treatment, has shown some wear reduction, but the data isn't consistent across all labs.
What about advanced polymers like PEEK?
We've looked at carbon fiber reinforced PEEK. It showed success in low-contact stress situations, like in a highly conforming mobile unicompartmental knee.
But this material comes with a major flashing red warning light.
Absolutely. There is grave concern about using CFR PEEK in high-contact stress applications, like a low-conforming or malaligned TKR. In those scenarios, it has showed disastrously high wear rates. The carbon fibers can get exposed and shear out, leading to highly abrasive accelerating wear.
So the takeaway is clear. The engineering decision has to precisely match the clinical environment.
You have to select the right tool for the job. We've spent decades solving material failure. We can't let material misuse bring us back to square one.
This has been an incredibly detailed deep dive. We've moved from the oxidized, high-conformity, failure-prone joints of the past to the sophisticated science of today. Let's synthesize the major advancements. We've transitioned from standard poly, which required high conformity, to the modern paradigm. Moderately cross-linked, stable material used in low-conformity designs.
And the result of that is profound. We have largely solved the material wear problem by chemically fortifying the UHMWPE. We're achieving wear rates in modern fixed-bearing knees that are now comparable to what we used to only see with complex mobile bearings.
But the analysis of all this data, the ISO wars, the sensitivity to motion, the liftoff findings, it all underscores the crucial importance of the simulation methodology itself.
It does. The sheer variation in reported wear rates under different conditions highlights why you have to review the test methodology.
You have to ask the hard questions.
You have to. If a company reports low wear, was it tested using a benign displacement control standard that artificially limited motion? Or were they using a rigorous, safer approach with high cross-shear and simulated liftoff? Methodology bias can make a poor implant look great.
So we arrive at the final provocative thought, tying the lab right back to our responsibilities on the operating table. The engineering lab has largely solved the material wear problem. So if long-term wear is now primarily driven by extreme, non-standard kinematics like liftoff or rotation caused by implant position or soft tissue imbalance, what percentage of long-term TKR success today depends more on perfect surgical technique and accurate soft tissue balancing than on the specific implant material itself?
It shifts the entire clinical focus, doesn't it? The engineering data forces us to confront that we've spent decades perfecting the polymer, but if that perfect part is then installed with a minor ligament imbalance or a subtle malrotation,
An imperfection that induces non-standard kinematic.
its inherent lifespan is instantly truncated by the cross-shear mechanism.
So minor surgical imperfections, or even a patient's off-label activities, might be setting the biological clock of an otherwise perfectly engineered implant far more quickly than we realize. It's a humbling and frankly terrifying responsibility for us in the OR.
It is. Thank you for this deep dive into tribology today. It just reinforces that the engineering constraints are the ultimate constraints on our surgical freedom.
Absolutely. That's something for you to mull over the next time you look at a tight medial collateral ligament.